In my earlier video, I had discussed about basis and dimension of range of linear transformation and null space of linear transformation. Just recall, I will recall this part by one picture because this topic is more important for any competitive exam. Actually, even though today's goal of this lecture is matrix representation of linear transformation, but at first I will see one nice picture to find basis of range T and null space of range T. Consider this is the vector space V with dimension n and this is the vector space W with dimension m. Consider phi1, phi2 up to phi t be the basis of null space of linear transformation. Now, extended this basis of the vector space V, consider u1, u2 up to un minus mu t be the extended basis of the vector space V. And this u1 map to v1, u2 map to v2 and un minus mu t map to vn minus mu t. And this is be the element of range T since v1, v2 up to vn minus mu t is the basis of range T. And this basis contains n minus mu t vectors. So, dimension of this range T is n minus mu t. And we all of us know dimension of range T is called as rank T. That implies rank T equal to n minus mu t. And from this line we can tell rank T plus mu t equal to n. Where mu t be the null space of the transformation because kernel T contains mu t vectors. So, rank T plus nullity T equal to dimension of V because dimension of V I have considered n. Okay, are you getting the picture? If you know the picture, then you will understand in better way. And this expression actually be the rank nullity theorem. In my earlier video, I have studied the rank nullity theorem. The theorem is, let V and W be finite dimensional vector space over the field F. Then, rank T and nullity T equal to dimension of V. Are you getting? This is actually the idea of rank nullity theorem. That means, by this expression, we can tell easily dimension of nullity T always less than equal to dimension of V and dimension of range T always less than equal to dimension of W. Because null space is a subspace of the vector space V and range space is a subspace of the vector space W. But from rank nullity theorem, I have got rank T plus nullity T equal to dimension of V. So, dimension of rank T cannot exist dimension of V. That means dimension of rank T cannot exist dimension of W as well as dimension of V. Since rank T cannot exist dimension V and dimension W, so there exists a nice theorem. Rank T always less than equal to minimum of dimension V and dimension W. And this theorem is more important for any competitive exam. Find rank of a linear transformation. And the result is such type, let A is matrix of order m cross n matrix. Then determine the rank of this matrix. We all of us know every finite dimensional linear transformation can be written as matrix. A is m cross n matrix, that means there exists a linear transformation T from Rn to Rm. So, rank of A always less than equal to minimum of the set M and N. As far example, if we consider A is 3 cross 5 matrix, now if we know the theorem, then we can easily find the rank of this matrix. Here, the rank of the matrix is minimum of Mn, means minimum of 3, 5. That means rank of A always would be less than equal to 3. And when rank of A equal to minimum of M, N, then this is actually the full rank of the matrix. Are you getting? Well, I will highly recommend you, please see and please pay attention in this topic, because this topic is more important for any competitive exam, not only CSN NET, IIT JAM, GATE, for all competitive exam and for higher study, this concept is more important. So, I am trying to clear this concept. Okay? I had seen in my earlier video, when a linear transformation be 1, 1, then rank T equal to dimension of V. Just see again, because here I will establish one nice property by this concept. If V and W be finite dimensional vector space and T is 1, 1 from V to W, then by Diagonality theorem we got rank T plus nullity equal to dimension of V. And if T is 1, 1, then nullity T equal to 0. That means rank T equal to obviously dimension of V. Okay. This I learned in my earlier video elaborately. That means if V and W be finite dimensional vector space and T mapping from V to W, if this is 1, 1, then kernel T equal to 0 and rank T equal to dimension of V. Okay. Picture is such type. Consider this is V and this is W. And there exists a linear transformation T from V to W. Here, consider the transformation be 1, 1. And consider this is the range T. Obviously, dimension of range T is rank T. Obviously, rank T less than equal to dimension of W. And since here I have considered the mapping is 1, 1, that means rank T equal to dimension of V. Okay. That means for 1, 1, always dimension of V less than equal to dimension of W. Hence, we cannot have any 1, 1 linear transformation from a vector space to lower dimensional vector space. This is easy method to find is a linear transformation be 1, 1 or on 2. For competitive exam, to find a linear transformation be 1, 1 or on 2, this is very important. So, I will highly recommend you, please see this video with pay attention. We consider dimension of V equal to N and dimension of W equal to M. Therefore, for 1, 1 linear transformation, always N less than equal to M. Are you getting? Well, now I will say similarly one rules to determine is a linear transformation be onto, and onto means we all of us know the range T equal to W. Then this transformation is onto and T is onto. That means dimension of range T equal to dimension of W means rank T is equal to dimension of W. And by Diagonality theorem, we all of us know rank T plus nullity T equal to dimension of V. Since here rank T plus addition nullity T equal to dimension of V, therefore rank T always less than equal to dimension of V. Here notice, since T is onto, then rank T equal to W. and here rank T less than equal to dimension of V. So if T is onto, then that implies dimension of W less than equal to dimension of V. Are you getting the condition? When T be onto? Since I have considered a dimension of V equal to N and dimension of W equal to M, that means linear transformation T is onto when dimension of W less than equal to dimension of V. That means M less than equal to N. And there exists a nice corollary. Consider dimension of V equal to N and dimension of W equal to M. And T be a linear transformation from V to W which is linear. If N greater than M, then T is not injective. And if M greater than N, then T is not surjective. Are you getting? What is the condition of linear transformation? To find is this mapping is 1, 1 or onto OL. Our next example, suppose T be a linear transformation from R4 to R7, which is linear. Then what is possible value of dimension of image T? And is the mapping is 1, 1? Now I will see at first what is the dimension of image T. Here notice T be linear transformation from R4 to R7. That means there exists a matrix of A with 7 cross 4. Okay. That imply rank of A less than equal to 4. That means possibility of image T would be either 0 or 1 or 2 or 3 or 4. Okay. By this formula we can tell obviously this mapping T cannot be onto because image T cannot be 7. Okay. Also by this formula we can tell T cannot be onto because here 7 greater than 4. Now I will check is this mapping is 1, 1. Here M equal to 7 and N equal to 4. Since 4 less than 7, so obviously by this formula there exists a 1, 1 mapping. But I will use another method to check 1, 1. I will see possibility of kernel of the matrix. Here rank of A plus nullity of A equal to 4. That means since possibility of rank of A is 0, 1, 2, 3 or 4. When rank of A equal to 0, then dimension of car A equal to 4. When 1, then car A equal to 3. When 2, then kernel of the matrix is 2. And when 3, then kernel of the matrix is 1. And when 4, then kernel of the matrix is 0. That means when kernel of the matrix is 0, then obviously this linear transformation be 1, 1. Are you getting the another method? OL. Let V and W be finite dimensional vector space over a field A. Then the transformation T which is mapped from V to W is called isomorphism of V onto W if T is both 1, 1 and onto. If such T exists, then we can say V is isomorphic to W. Suppose V is isomorphic to W. If there exists a linear transformation T from V to W such that T is 1, 1 and onto. That implies dimension of V equal to dimension of W. And when dimension of V not equal to dimension of W, that means V cannot be isomorphic to W. Are you getting the idea? I hope my all viewers have understood. Linear transformation be isomorphism when 1, 1, when onto. This type of example is more important for any competitive exam. There exists a simple property. If dimension of V equal to dimension of W, is it necessary V is isomorphic to W? When there exists a linear transformation T from V to W, then T is onto, that always imply T is 1 1. Because T is onto if and only range T equal to W. And range T equal to W, that imply obviously rank T equal to dimension of W. And by the rank nullity theorem, we can tell, since rank T equal to dimension of W, that means by rank nullity theorem, nullity T equal to 0. And since nullity T equal contain only 0 vector, that means obviously T is 1 1. That means in linear transformation, onto always imply 1 1. Also 1 1 always imply onto. This is the if and only if condition. That means if T is isomorphic to V to W, it is enough to check if T is onto or T is 1 1. So it is not necessary condition. V is, if dimension of V equal to dimension of W, that does not always imply V is isomorphic to W. When T is 1 1 also or onto also, then we can tell this two vector space means V and W be isomorphic to each other. Are you getting? Now let's come back our original discussion, matrix representation. Let us investigate what is matrix representation. Here, consider dimension of V and dimension of W equal to both dimension be n, and choose an ordered basis BV as V1, V2, Vn for the vector space V. Now choose another ordered basis for BW, W1, W2 up to Wn. Here the mapping is such type. Here this is the ordered basis of the vector space V and this is the ordered basis of the vector space W. The mapping is such type: V1 map to W1, V2 map to W2 and Vn map to Wn. So first define T as TV1 equal to W1, TV2 equal to W2 and Tvn equal to Wn. Now suppose consider any vector x from V and we can write any vector as unique linear combination of this basis vector such as x equal to x1 v1 plus x2 v2 up to xn vn. Here this is the basis vector of bv. Now apply t on this equation both sides, then tx would be t of x1 v1 plus x2 v2 up to xn vn, and since t is a linear, so this means t of x1 v1 plus t of x2 v2 up to t of xn vn. And here by the property of multiply with any vector by scalar, this is equal to x1 times tv1 plus x2 times tv2 up to xn times tvn. We all of us know this process. Now just put the value tv1 equal to w1 plus x2, tv2 equal to w2 plus up to xn, tvn equal to wn. Obviously this transformation is linear transformation and this is the isomorphism because here dimension of v equal to dimension of w and here dimension of range t. Since this is the basis of w, that means obviously dimension of range t equal to would be same as dimension of w. So obviously t is onto, and since t is onto, so obviously the mapping is 1 1. So there exists a isomorphism from v to w. Here the isomorphism as with respect to ordered basis. Are you getting? OH. Now let's say for this, let's see how do we find the transformation with respect to basis vector E. For this, consider a linear operator T from V to V and consider the basis for the vector space V such as U1, U2 up to En. Then T U1 equal to, obviously this is equal to W1. That means here W1 is written as combination of this basis vector. Now similarly T of E2 equal to W2 and written W2 as combination of this basis vector. This is actually A1 to E1, A2 to plus A2 to E2 plus up to AN to En. And if we consider this process, then T of UN would be Wn, and this is actually equal to A1n U1 plus A2n E2 up to ANn En. And now take the transpose of this coefficient as a matrix. That means transpose of this coefficient would be such type: A11, A21, AN1 as a first column vector, A12, A22, AN2 as a second column vector, up to A1n, A2n, ANn as a nth column vector. That means here this A be the written as the basis vector with respect to the basis E. Okay, actual picture is of this transformation, because today's video I have defined all thing by picture. So this picture would be x maps to tx, where tx written as a times x with the standard basis of V, and here the given matrix transformation with respect to this standard basis. Now consider another basis of vector space V. This is not standard basis. Then with respect to this basis, the linear transformation is such type. See, here consider this basis as V1 times x with respect to this V1. This is the picture of matrix representation. Let's say one consider example. A linear transformation T from R3x to R3x such that Tpx equal to P prime x. Here choose the standard basis 1x, x squared, x cube. Consider 1 as a E1, x as a E2, x squared as a E3 and x cube as a E4. And consider the polynomial x px equal to ax cube plus bx squared plus cx plus d. Then apply this basis vector, then T1 would be 0, which is actually written as 0 times x cube plus 0 times x squared plus 0 times x plus 0. And T of x equal to 1, which is equal to 0 times x cube plus 0 times x squared plus 0 times x plus 1. And T of x square equal to 2x square, which is written as 0 times x square cube plus 0 times x square, sorry here not x square, here x plus 2 times x plus 0. And T of x cube would be 3x square, which is written as 0 times x cube plus 3 times x square plus 0 times x plus 0. Therefore, the matrix representation would be just written as the coefficient as a transpose. That means this would be 0, 0, 0, 0 for this row. Here this would be column as a column vector. Then for this 0, 0, 0, 1. For this 0, 0, 2, 0. And for this would be 0, 3, 0, 0. This is the matrix representation with respect to this standard basis. Are you getting? How we have to find any linear transformation? By a matrix representation? Oh well. Consider one similar type example D from P3 to P2 and the operator is such type D of P equal to P prime. Here basis vector of P3 is written as 1t t square t cube and basis vector of P2 is written as 1t t square. Therefore, here we have to find matrix A with respect to these two basis vector B1 to B2. This is difference. Here I have considered two basis vector. For this, just consider the basis vector of B1 as P0 equal to 1, P1 equal to T, P2 equal to T square and P3 equal to T cube. And this basis vector as like Q0 equal to 1, Q1 equal to T and Q2 equal to T square. Then dP0 would be, since the matrix is operator is defined as P prime, then this would be 0. Then we can write it as 0 times Q0 plus 0 times Q1 plus 0 times Q2. And dP1 would be 1, which we can write it as 1 times Q0 plus 0 times Q1 plus 0 times Q2. And dP2 would be 2t, which we can write as 0 times Q0 plus 2 times Q1 plus 0 times Q2. And dP3 would be 3t square, which we can write as 0 times Q0 plus 0 times Q1 plus 3 times Q2. Therefore, the matrix A with respect to these two bases B2 with B1 would be just written as a column 0 0 0 1 0 0 0 2 0 0 0 3. Are you getting the matrix? Here difference, here the basis vector, I have considered two basis vector, one from codomain and one from domain. Are you getting? Oh well. Today I will stop here, but I will highly recommend you, please see today's video with pay attention. In my next video, I will discuss this topic elaborately. See you soon. Stay safe and stay positive always. And don't forget to subscribe my channel. Thank you so much.